Why is it impossible to travel to Uranus and Proxima Centauri? This question contains an uncomfortable truth that humanity prefers to ignore. We are trapped in a minuscule corner of the cosmos, contemplating from a distance destinations that we can never reach with our own hands. For decades, we have dreamed of exploring the confines of the solar system and venturing towards the neighboring stars. But the reality is brutally simple. The laws of physics have condemned us to be eternal observers, never travelers. The distances involved are not merely great, they are incomprehensibly vast, measured in billions of kilometers to Uranus and trillions to Proxima Centauri. Our fastest spacecraft, those that represent the pinnacle of our engineering, move at speeds that are pathetically slow on the cosmic scale, requiring decades just to reach the outer planets of our own planetary neighborhood. The lethal radiation that saturates deep space, the total absence of sufficient fuel, the unrelenting time that destroys both machines and human bodies, all these obstacles converge to create an invisible, yet absolutely insurmountable barrier. But there is something even more unsettling than these technical limitations. Even if we were to overcome every one of these monumental challenges, even if we developed revolutionary technologies that today exist only in our imagination, the distances involved are so monumental that they would turn any mission into a one-way trip into nothingness. The astronauts who departed would never see Earth again. Their communications would take hours or years, arrive, and any technical problem would mean a solitary death in the absolute vacuum of space. This is the raw reality of our place in the universe. We can look, we can dream, but we cannot touch what we see shining in the nocturnal darkness. Every telescope we point towards Uranus or Proxima Centauri reminds us of our status as cosmic prisoners, confined by fundamental forces of the universe that no human technology can conquer. The tyranny of distance and time-maze, we explore these fascinating and terrifying impossibilities to truly understand why Uranus and Proxima Centauri are impossible destinations. We must first confront a reality that our human minds struggle to process. Distances in space are not like distances on Earth. They are not simply larger numbers on a map. They are abysses, so profound, so incomprehensibly vast that they defy all human intuition, developed over millions of years of evolution on a small planet. When we look at the night sky and see those points of light, our brain perceives them as if they were just up there, perhaps a few kilometers away. But the truth is that each of those points represents distances so monumental that if we tried to walk toward them, we would consume not just one lifetime, but millions of human lives, chained one after another. Let us begin with Uranus, the seventh planet from the Sun, that ice giant that we can barely distinguish as a greenish-blue dot, even with our best telescopes. Uranus orbits at an average distance of 2,800,000,000 kilometers from the Sunday. To put this into perspective, the distance between the Earth and the Sun is approximately 150 million kilometers, a measure that astronomers call 1 astronomical unit. This means that Uranus is 19 times farther from the Sun than we are. But these numbers, however large they may seem, still do not capture the real magnitude of the problem. Imagine driving a car at 100 kilometers per hour without ever stopping. To reach Uranus, you would need to drive continuously for 3,200 years, 3 complete millennia at the wheel, traversing entire generations of human history, and you still would not have arrived. Now, if Uranus represents a monumental abyss, Proxima Centauri is something else entirely. It is a leap into the truly incomprehensible. Proxima Centauri, our closest neighboring star after the Sun, is located 4 light-years away. A light-year is the distance that light travels in 1 year, moving at 300,000 kilometers per second. That is equivalent to 9,460 billion kilometers for every light year. Multiplied by 4.2, we obtain approximately 40 trillion kilometers to Proxima Centauri. This number is so absurdly large that it loses all practical meaning for our minds. If you could drive that same car at 100 kilometers per hour towards Proxima Centauri, you would need 45 million years to arrive. The entire human evolution, since we separated from our common ancestors with chimpanzees until today, has taken only 6 million years. To make these distances even more tangible, imagine that the Sun is the size of a basketball placed in the center of a city. On this reduced scale, Earth would be a small marble 15 meters away. Mars would be at 23 meters. Jupiter, the gas giant, would be 78 meters from the Sun. But Uranus, on this same scale, would be 287 meters away, nearly 3 complete football fields from your solar basketball. And Proxima Centauri, our closest stellar neighbor, would be at 4,000 kilometers away on this scale. If your Sun is a basketball in Madrid, Proxima Centauri would be near Istanbul, and that is just the closest star. The next closest would be even farther away. Voyager 2, the only spacecraft that has visited Uranus in all of human history, took 9 years to reach it after its launch in 1977. 9 years of continuous travel through the vacuum, taking advantage of favorable planetary alignments that only occur once every 175 years, using the gravity of Jupiter and Saturn as cosmic slingshots to increase its speed. Without those gravitational assists, the journey would have taken double or triple the time. And Voyager 2 is one of the fastest spacecraft we have ever built, traveling at more than 60,000 kilometers per hour. Even at that dizzying speed, crossing the solar system to Uranus required almost a full decade. Imagine spending 9 years locked in a closet-sized capsule, never being able to leave, seeing only darkness through the window, with no gravity, no fresh air, no possibility of turning back if something goes wrong. But the true horror emerges when we apply these numbers to Proxima Centauri. The same Voyager 2, traveling at its current speed, would take approximately 73,000 years to reach Proxima Centauri if it could travel in a straight line toward it, which it cannot. 73 millennia is more time than all of human civilization has existed. When Voyager 2 finally arrived, if any component was still functioning, the cultures that launched it would have vanished eons ago, replaced by completely different societies that probably would not even remember that we ever sent that spacecraft. The very concept of humanity might have evolved into something unrecognizable, and all this assumes that the spacecraft would somehow survive intact for all that time, which is impossible for reasons we will explore later. Between the billions of kilometers that separate our world from these distant destinations, there is nothing, only absolute vacuum. There are no service stations to refuel, no ports for repairs, no islands for rest, only infinite darkness occasionally peppered with microscopic grains of space dust traveling at lethal velocities. Every centimeter of that journey must be planned. Every gram of fuel must be carried from the start. Every spare part must fit into the limited cargo space, and the farther you want to go, the more fuel you need. This makes your spacecraft heavier, which requires even more fuel, in an exponential equation, without a practical solution. This is the cruel paradox of space travel. The most interesting destinations are precisely those that are permanently out of our reach. When ancient terrestrial explorers set out for unknown lands, they knew the world was finite. They knew that if they sailed long enough, they would eventually reach somewhere. But space explorers face a different reality. They can travel for their entire lives and never reach anywhere. They can burn all their fuel and barely move an inch on the cosmic scale. And most terrifying of all, there is no way to cheat these distances. There are no shortcuts in space. There are no shorter alternative routes. The universe is indifferent to our ambitions, and the distances that separate us from distant worlds will remain exactly as vast, no matter how much technological progress we achieve. This is the first insurmountable wall that keeps us prisoners in our small cosmic corner, pure, ruthless, absolute distance, the absolute barrier of the speed of light in the universe. Speed is not just a technical challenge, it is a fundamental law that governs everything that exists, an invisible barrier carved into the very fabric of space and time. The speed of light, 300,000 kilometers per second, is not simply the speed limit of the cosmos. It is an absolute wall imposed by physics that no amount of engineering or innovation can break down. Albert Einstein demonstrated in 1905 that nothing with mass can reach or exceed this speed, and every experiment conducted since then has confirmed this immutable truth. But the problem is not just that we cannot travel at the speed of light. The problem is that our most advanced spacecraft move at speeds so ridiculously slow in comparison that they could be considered practically immobile on the cosmic scale. The Parker Solar Probe from NASA, launched in 2018, currently holds the record as the fastest object ever built by a human being. In September of 2023, it reached an astonishing speed of 635,000 kilometers per hour as it approached the Sun. To put this into perspective, at that speed, you could travel from New York to Los Angeles in only 30 seconds. You could orbit the entire Earth 15 times in 1 hour. It is a speed that defies all everyday human experience, faster than anything we have experienced on the surface of our planet. However, when we compare these 635,000 kilometers per hour with the speed of light, 1,080,000,000 kilometers per hour, we discover a devastating truth. The Parker Solar Probe travels at 0.05% of the speed of light, not even a tenth of 1%. It is like comparing the speed of a snail with that of a fighter jet. And this record speed of the Parker is not something that can be maintained indefinitely or applied to interplanetary travel. The probe reaches these extreme velocities only when it plunges into the intense gravitational well of the Sun, using the immense gravity of our star as a natural cosmic slingshot. It is free, gravitational acceleration, not propulsion generated by engines. Once away from the Sun, the speed decreases dramatically due to orbital physics. The Voyager 1 and 2 probes, launched in 1977 and currently moving away from the solar system toward interstellar space, travel at much more modest speeds of approximately 60,000, 1,000 kilometers per hour. After more than 45 years of continuous travel, Voyager 1 is barely 23 billion kilometers from Earth, a distance that light crosses in only 21 hours. What light covers in less than a day, Voyager has needed almost half a century to traverse. Now, let us apply these speeds to our impossible destinations. Uranus orbits 2,800,000,000 kilometers from the Sun. Voyager 2 took 9 years to reach it, taking advantage of an exceptional planetary alignment that only occurs every 175 years. Without those gravitational assists from Jupiter and Saturn, which acted as cosmic slingshots to increase its speed, the journey would have required between 20 and 30 years or more. Imagine sending human astronauts on a 30-year one-way mission to Uranus. Astronauts who departed at 30 years of age would be 60 when they arrived, assuming they survived the journey, which is extraordinarily improbable for reasons we will explore later. And that is just to get to Uranus, a planet within our own solar system, relatively close in cosmic terms. But when we turn our attention toward Proxima Centauri, the figures cross the line between difficult and completely absurd. At 4.2 light-years away, Proxima Centauri is 40 trillion kilometers distant from us. If we could send a spacecraft at the current speed of the Parker Solar Probe, 635,000 kilometers per hour, at its fastest point, it would take approximately 7,000 years to arrive 7 complete millennia. All of recorded human civilization, from the first cities in Mesopotamia to modern skyscrapers, has existed for less time than that, and no one builds a spacecraft that can function for 7,000 years. Technology degrades, systems fail, radiation damages, electronic components. Even the Voyager probes, the most durable objects we have ever sent into space, will begin to run out of power in the 2030s, barely 50 years after their launch. Voyager 1, currently moving away from the solar system at 17 kilometers per second, would take 73,000 years to reach Proxima Centauri if it could travel in a straight line toward it. 73 millennia, during which humanity would have evolved beyond recognition. During that time, entire civilizations could arise and collapse. The languages we speak today would be as unintelligible to our descendants as the grunts of our prehistoric ancestors are to us. Earth itself could have suffered glaciations, mass extinctions, or climate changes so profound that the planet would be unrecognizable. And all this, while a small, solitary probe, if any component is still functioning, slowly crawls through the endless vacuum toward a distant star. The fundamental problem is that reaching significant speeds in space requires astronomical amounts of energy. Kinetic energy increases with the square of the velocity, which means that doubling your speed requires 4 times more energy. Tripling it requires 9 times more energy, and as you approach the speed of light, the amount of energy necessary approaches infinity due to the relativistic effects described by Einstein. To accelerate even a small 1-ton spacecraft to 10% of the speed of light, you would need energy equivalent to the entire electrical output of the United States for several years, and that is just to accelerate. Then, you would need a similar amount of energy to decelerate upon arrival at your destination, unless you plan to crash at a fraction of the speed of light, which is obviously not ideal. Some have proposed using nuclear propulsion, ion engines, or even giant solar sails to reach greater speeds, and in theory, these technologies could work better than traditional chemical rockets. A solar sail, propelled by powerful terrestrial lasers, could in principle reach 20% of the speed of light. At that speed, you would reach Proxima Centauri in 21 years, a time that begins to look almost feasible for a generational mission. But the engineering challenges are monumental. You would need sails the size of entire countries, made of materials thinner than paper, but capable of withstanding the pressure of radiation. You would need lasers in Earth orbit, with powers equivalent to complete nuclear power plants, and once accelerated, the spacecraft would have no way to brake upon arrival, passing Proxima Centauri at a fraction of the speed of light in a matter of minutes before disappearing forever into the interstellar vacuum. The uncomfortable truth is that the speed necessary to make interstellar travel viable permanently out of our reach. It is not a matter of waiting a few centuries until technology improves. It is a fundamental limitation imposed by the laws of physics that govern our universe. We can dream of warp drives that bend space-time, of wormholes that connect distant points of the cosmos, of extra dimensions that provide shortcuts through the universe. But all these concepts remain firmly in the realm of theoretical speculation, with no clear path from theory to practical engineering. Meanwhile, our fastest spacecraft crawl through the solar system at speeds that would be insultingly slow for any interstellar journey, constantly reminding us that we are prisoners not only of space, but also of time itself. Uranus, the undescendable ice giant. Beyond the icy confines of the outer solar system, where the sun's light arrives faint and ghost-like, orbits one of the strangest and most hostile worlds we know, Uranus. The seventh planet from the Sun is not simply another gas giant. It is a world that defies all planetary rules, a place so extreme that it makes Earth's most lethal environments seem like cozy gardens by comparison. Uranus is a planet that literally rolls on its side as it orbits the Sun, with its axis of rotation tilted 98 degrees, causing its poles to point alternately toward our star during its long year of 84 terrestrial years. This means that each pole experiences 42 years of continuous sunlight, followed by 42 years of absolute darkness, creating weather patterns so bizarre that they defy comprehension. Uranus's atmosphere is a chemical nightmare, composed primarily of hydrogen and helium, with approximately 2.3% methane that gives it that characteristic pale greenish-blue color we see from Earth. But beneath that apparently calm upper layer, the planet hides terrifying secrets. Temperatures in the upper atmosphere drop to negative 224 degrees Celsius, making Uranus the coldest planet in the solar system, despite Neptune being farther from the Sun. This extreme temperature turns atmospheric methane into ice, creating frozen crystals that float in the upper layers. Descending through this atmosphere would be like plunging into a toxic, frozen ocean, where every breath would be impossible, and every second would bring one closer to an inevitable death by freezing and crushing. But the true horror of Uranus is not in its outer atmosphere, but in what lies beneath. Unlike Jupiter and Saturn, which are primarily compressed hydrogen and helium, Uranus is what astronomers call an ice giant. Beneath its atmosphere exists an immense mantle composed of water, methane, and ammonia, in strange states of matter that do not naturally exist on Earth. Under the monumental pressures of the planet's interior, thousands of times the terrestrial atmospheric pressure, these materials form superionic fluids, exotic states, where water remains liquid at temperatures of several thousand degrees. It is water that burns, methane that flows like lava, ammonia compressed to unimaginable densities, and, at the very center of the planet, there might exist a rocky core, the size of Earth, crushed under pressures so extreme that they would instantly turn any material into dust. The only spacecraft that has visited Uranus in all of human history was Voyager 2 in January of 1986. After 9 years of travel from Earth, taking advantage of gravitational assists from Jupiter and Saturn that are only possible once every 175 years, Voyager passed by Uranus at a distance of 81,500 kilometers from its upper clouds. That encounter lasted barely a few hours, a cosmic blink during which the probe captured images and data while passing at full speed, with no capacity to brake or enter orbit. Since then, no other spacecraft has returned. No mission is planned. Uranus remains a world observed only from immense distance, studied only through telescopes that can barely distinguish details on its nebulous surface. And there are profound reasons why no space agency has attempted to send another mission to Uranus. The journey is simply too long, too costly, too risky. Even with the most efficient trajectories and perfectly calculated gravitational assists, a spacecraft would take at least 9 years to arrive, and that is just one way. A crewed mission would be a journey of decades, with no guaranteed return. Astronauts who departed for Uranus in their 20s or 30s would be middle-aged or elderly people when they finally arrived, assuming they survived the journey. which is extraordinarily improbable given the dangers of deep space. During those 9 years or more, they would be completely isolated, farther from home than any human being in history, with no possibility of rescue if something went wrong. And in space, something can always go wrong. Distance is not just an abstract number on paper. It is time. It is fuel. It is accumulated radiation. It is systems that fail. It is food that must last for years. It is water that must be recycled thousands of times. It is air that must be continuously filtered. It is human psychology subjected to stress beyond anything experienced on Earth. Astronauts on the International Space Station typically remain 6 months in orbit before returning home, and many report psychological difficulties even in that relatively short period. Imagine multiplying that time by 20. Imagine watching Earth turn into a pale blue dot, indistinguishable from the stars around it. Imagine knowing that there is no way to return quickly, that any medical emergency would be a death sentence, that any critical system failure would mean floating forever in a metal coffin through the vacuum. And all this to arrive at a planet where you could not even land if you wanted to. Uranus has no solid surface. It is a gas giant where the atmosphere simply becomes gradually denser until it turns into that superionic ocean of exotic materials. There is no place to stand. There is no solid ground to plant a flag. Any spacecraft attempting to descend would be crushed by increasing pressures long before reaching the planet's hypothetical rocky core. You would be compressed like a soda can, your atoms pushed together until you ceased to exist as a distinguishable entity. The planet would consume you without record, without trace, as if you had never been there. Uranus is a world that can only be observed from a distance, never touched, never explored directly. It is a distant giant that reminds us of our fragility and the absolute limits of our capacity for exploration. The tyrannical fuel equation. When most people think of space travel, they imagine gleaming spacecraft sailing through the cosmos like ships navigating terrestrial oceans. But this analogy is dangerously misleading because it hides the most fundamental and devastating problem of all long-distance space travel: the tyrannical equation of fuel. Unlike a ship that can passively float on the water, a spacecraft must carry with it every gram of fuel necessary to accelerate, maneuver, and eventually decelerate. There are no ocean currents to take advantage of. There are no winds to push your sails. Only the absolute vacuum, where every change in speed requires burning precious fuel that must have been loaded at the beginning of the journey. And here arises the cruel paradox that makes interplanetary and interstellar travel practically impossible. The fundamental equation is simple but devastating. The more fuel you carry to go faster and farther, the heavier your spacecraft becomes. But a heavier spacecraft requires even more fuel to accelerate it to the desired speed. This additional fuel adds more weight, requiring even more fuel in an exponential spiral that quickly escapes any practical control. Engineers call this the Tsiolkovsky rocket equation, first formulated by the Russian scientist Konstantin Tsiolkovsky in 1897. This mathematical equation describes with implacable precision how the final velocity of a rocket depends exponentially on the fraction of mass, that is, fuel versus payload. And the numbers that emerge from this equation are absolutely disheartening. Consider a concrete example: the Saturn V rockets, which carried astronauts to the moon during the Apollo program, weighed 3 million kilograms at launch. Of that colossal mass, 2,755,000 kilograms were fuel. Only 45,000 kilograms were the capsule, lunar module, astronauts, and provisions. This means that 95% of the total mass at launch was fuel, and only 5% was payload. And this was for a relatively short 3-day trip to the Moon, our closest cosmic neighbor, located only 384,000 kilometers away. The Saturn V did not have enough fuel to return. That is why the lunar module used a separate, smaller engine that had been carried all the way from Earth. Every gram counted. Every extra kilogram of fuel required more robust systems to contain it, stronger structures to support it all, adding more mass in an implacable cascade. Now, extrapolate these numbers to Uranus, 2,800,000,000 kilometers away, more than 7,000 times farther than the Moon. To reach Uranus in a reasonable time, say 5 years instead of 9, you would need much greater speeds than those used in the Apollo missions. You would need to accelerate continuously for weeks or months, reaching speeds of hundreds of thousands of kilometers per hour. And then, crucially, you would need to decelerate upon arrival to enter orbit around Uranus instead of flying past as Voyager did. Decelerating requires as much energy as accelerating, effectively doubling your fuel needs. Quick calculations suggest that you would need more than 99.9% of your initial mass to be fuel, leaving barely a fraction of a percent for the spacecraft itself, the astronauts, the food, the water, the life support systems. It is mathematically impossible with conventional chemical rockets. Some have proposed using nuclear propulsion or ion engines to solve this problem, and in theory, these technologies are more efficient than traditional chemical rockets. An ion engine expels charged particles at much higher speeds than the hot gases of a chemical rocket, providing more thrust per kilogram of fuel. But even with these advanced technologies, the improvements are incremental, not revolutionary. An ion engine might reduce your fuel requirements by a factor of 3 or 5, which sounds impressive until you realize that you would still need to carry hundreds of tons of fuel for a trip to Uranus. And ion engines have their own set of problems. They produce extremely low thrust, requiring years of continuous acceleration to reach significant speeds. Years during which the engine must operate perfectly without failure, something no human-made machine has ever achieved. Nuclear propulsion offers even more energy per kilogram of fuel. Fissioning uranium or plutonium atoms releases millions of times more energy than burning chemical fuels. In principle, a space nuclear reactor could provide the necessary thrust for long-distance missions while carrying significantly less fuel. But nuclear reactors are heavy, complex, and dangerous. You need massive shielding to protect the crew from radiation, elaborate cooling systems to dissipate heat in the vacuum where there is no air for convection, and redundant mechanisms to prevent catastrophic meltdowns. All this equipment adds thousands of kilograms of mass, eroding the theoretical advantages of nuclear propulsion. And then there is the small problem of launching radioactive nuclear material on a rocket that has a non-trivial probability of exploding during takeoff, scattering plutonium over a wide area. The political and security implications make this option practically unviable. Even if we somehow overcame all these technical and political challenges, we still face the fundamental problem that space is vast, and our spacecraft are pathetically slow. To reach Proxima Centauri, you would need speeds, not of thousands, but of tens or hundreds of thousands of kilometers per second, a significant fraction of the speed of light. No known propulsion system can provide this. Antimatter propulsion, where matter and antimatter annihilate each other, converting into pure energy, according to Einstein's famous equation, $ext E equals ext mc circumflex, $2, theoretically, offers the highest possible efficiency. But producing antimatter requires monumental amounts of energy, more energy than you get from annihilating it. It is a net energy sink, and storing antimatter is extraordinarily difficult because it annihilates instantly upon contact with normal matter. You would need perfect magnetic fields maintained by systems that cannot fail for even a microsecond during years or decades of travel. A single failure means instant annihilation of your entire spacecraft and crew in a flash of gamma radiation. The fuel trap is not an engineering problem awaiting a technological solution. It is a fundamental consequence of the laws of physics that govern our universe. Every kilogram you carry must be accelerated and decelerated. Every meter per second of speed requires energy, and that energy must come from somewhere, must be stored in some form, must be transported from the beginning. There is no way to escape this reality. There is no ingenious trick that avoids it. The mathematics are implacable, and the mathematics clearly state that travel to destinations like Uranus, and especially Proxima Centauri, is permanently out of our reach with any propulsion technology based on carrying fuel. We are trapped not only by distance and time, but by the tyrannical fuel equation that turns our cosmic ambitions into mathematically impossible dreams. Proxima Centauri, the cruelest illusion of proximity, beyond the confines of our solar system, across an abyss of darkness so vast that it defies all human comprehension, faintly shines a red dwarf star called Proxima Centauri. It is our closest stellar neighbor after the Sun, a title that suggests proximity and accessibility. But this closeness is a cruel illusion of cosmic perspective. Proxima Centauri is located 4.2 light-years away, approximately 40 trillion kilometers, a distance so incomprehensibly vast that even light, traveling at 300,000 kilometers per second, needs 4 years and 2 months to cross it. And let us remember that light is the fastest thing that exists in the universe. Nothing with mass can reach that speed, which means that any spacecraft we build will need much more than 4 years to arrive, probably decades, centuries, or millennia, depending on the available technology. Proxima Centauri is an $XM class red dwarf star, significantly smaller and cooler than our Sun. Its mass is barely 12% of the solar mass, and its radius only 14% of the Sun's radius. If you could put Proxima Centauri next to the Sun, it would look tiny by comparison, a faint ember next to a bright bonfire. But this deceptive smallness hides a fascinating fact. Proxima Centauri will probably live much longer than our Sunday. Red dwarf stars burn their hydrogen fuel so slowly that they can shine for trillions of years, far beyond the current age of the universe of 13.8 billion years. When our Sun expands into a red giant and consumes Earth in approximately 5 billion years, Proxima Centauri will have barely begun its long life. And the most exciting thing is that Proxima Centauri is not alone. Orbiting this faint star are at least 2 confirmed planets, possibly more. Proxima Centauri XB, discovered in 2016, is a rocky world with approximately 1.3 times the mass of Earth. It orbits its star every 11.2 days at a distance of only 7,500,000 kilometers, much closer to its star than Mercury is to the Sun. But because Proxima Centauri is so faint and cool, this proximity places Proxima Centauri EXB in the habitable zone, where temperatures could allow liquid water on the surface. It could have oceans. It could have an atmosphere. It could, in principle, harbor life. It is the closest, potentially habitable exoplanet to Earth that we know. A world where humanity could theoretically establish colonies if we could reach it. But here, the crucial word is theoretically, because the distance to Proxima Centauri turns any crewed mission into an exercise in mathematical futility. With our current fastest spacecraft, like the Voyager probes, traveling at 17 kilometers per second, we would reach Proxima Centauri in approximately 73,000 years, 73 millennia, during which entire civilizations would arise and collapse on Earth. During that time, humanity itself could evolve into something unrecognizable. The languages we speak would be forgotten, replaced by languages that do not yet exist. Current nations and cultures would be dust of ancient history. And meanwhile, a small, solitary probe would crawl through the interstellar vacuum, its systems, long since failed, its energy depleted, turned into nothing more than a fragment of dead metal, drifting forever between the stars. Even with proposed technologies, like solar sails, propelled by powerful lasers, the figures barely improve to levels we could call feasible. The Breakthrough Starshot project, proposed in 2016 by physicist Stephen Hawking and entrepreneur Yuri Milner, envisions thousands of tiny spacecraft, the size of postage stamps, each equipped with extremely thin graphene sails. Massive terrestrial lasers with combined powers of 100 gigawatts, equivalent to the output of 100 nuclear reactors, would bombard these sails with light for minutes, accelerating them to 20% of the speed of light. At that dizzying speed, the mini-probes would reach Proxima Centauri in approximately 20 years. 20 years sounds almost feasible until you consider the implications. First, these probes would be so small that they could barely carry basic instrumentation. There would be no crew. There would be no capacity to transmit more than minimal trickles of data. Second, traveling at 20% of the speed of light means that every particle of interstellar dust you encounter would impact with the energy of a small bomb. The space between stars is not completely empty. It contains approximately 1 atom per cubic centimeter. At relativistic speeds, these scattered atoms become lethal projectiles that would pierce any shielding. Third, and perhaps most devastatingly, once accelerated, these probes have no way to brake. They would fly past Proxima Centauri at a fraction of the speed of light, having barely minutes or hours to collect data before disappearing forever into the interstellar vacuum beyond. And all this assumes that the technology works perfectly, that the lasers can focus with enough precision on stamp-sized targets millions of kilometers away, that the sails do not tear or deform, that the system survived 2 decades of travel without maintenance. For a crewed mission, you would need something much larger and more complex. You would need a spacecraft the size of a small city to transport all the life support, fuel, radiation shielding, and provisions necessary for decades or centuries of travel. You would need closed ecosystems that recycle air, water, and nutrients perfectly for generations. You would need the capacity for reproduction to replace crew that ages and dies during the journey. It would be a generational ship where those who depart would never see the destination, only their great-grandchildren or great-great-grandchildren. And upon arrival, they could not return. It would be an absolute one-way trip, turning those astronauts into permanent cosmic exiles, forever cut off from the Earth they knew. Any mission to Proxima Centauri would not be exploration. It would be suicidal colonization, with no possibility of rescue or return. The distance to Proxima Centauri is a cosmic sentence that locks us into our solar system as effectively as if there were steel walls surrounding the Sun. We can look, we can detect its planets with sophisticated telescopes, we can speculate about alien life on worlds we will never touch. But all this observation and speculation do not change the fundamental reality. Proxima Centauri is permanently out of our reach. It is not a matter of waiting for better rockets or more efficient engines. It is a direct consequence of the structure of space-time and the laws of physics that simply do not allow objects with mass to travel fast enough to make interstellar travel viable. Proxima Centauri will shine there, so close in galactic terms, but so infinitely distant in practical terms, forever reminding us that the universe is incomprehensibly vast, and we are incomprehensibly small and slow. The lethal curtain of cosmic radiation space is not the inert, peaceful vacuum we imagine when we look at the stars on a quiet night. It is a hostile environment, saturated with lethal radiation that constantly bombards everything that exists outside the protection of planetary atmospheres and magnetic fields. On Earth, we are protected by two invisible yet absolutely critical shields: our atmosphere, which absorbs most of the harmful solar radiation, and the terrestrial magnetic field, which deflects deadly charged particles from the solar wind. Without these two natural shields, complex life on the terrestrial surface would be completely impossible. Every cell in your body would be constantly bombarded by radiation that would destroy your DNA, cause massive cancers, and kill you in a matter of weeks or months. And this is exactly what astronauts would face on any long-duration journey beyond low Earth orbit. Space radiation comes from multiple sources, each deadly on its own. First, are galactic cosmic rays, high-energy particles, accelerated by distant supernova explosions to near-light speeds. These particles, mainly protons and heavy atomic nuclei, travel through space for millions of years until they randomly impact anything in their path. When a galactic cosmic ray hits a human cell, it does not simply damage the DNA, as the sun's ultraviolet radiation would. It literally tears the DNA molecule apart, breaking it into multiple fragments and creating a cascade of secondary particles that cause additional damage. A single cosmic ray can traverse your entire body, leaving a trail of cellular devastation. And these impacts happen constantly, every second of every day, in deep space. Then there is the solar wind, a constant flow of charged particles ejected by the sun at speeds of hundreds of kilometers per second. The solar wind primarily contains energetic protons and electrons that, although less individually destructive than galactic cosmic rays, are much more abundant. They continuously bombard any spacecraft beyond the terrestrial magnetosphere. During solar storms, when the sun ejects massive coronal mass ejections of magnetized plasma, the intensity of the solar wind can increase dramatically. A major solar storm could deliver a lethal dose of radiation to unprotected astronauts in a matter of hours. And these storms are unpredictable. They can occur with little or no warning, especially during periods of maximum solar activity, which happen approximately every 11 years. Astronauts on the International Space Station, orbiting only 400 kilometers above the Earth's surface, are still partially protected by the terrestrial magnetic field and receive approximately 50 times more radiation than a person on the surface. During their 6-month stays, they accumulate radiation doses equivalent to several years of natural exposure on Earth. This significantly increases their long-term risk of cancer, but they are relatively close to home and can take refuge in more shielded sections of the station during solar storms. Now, imagine a 9-year trip to Uranus or a 20-year trip to Proxima Centauri. If we somehow achieved 20% of the speed of light, astronauts would be completely exposed to space radiation without protection for decades. Radiation shielding is extraordinarily difficult in space for one fundamental reason: mass. Materials that effectively block radiation, such as lead or water, are heavy. To adequately protect a crew during a years-long journey, you would need walls of several meters thick of water or hydrogen-rich plastic surrounding the entire habitat. This would add thousands or tens of thousands of tons of mass to your spacecraft, requiring astronomical amounts of additional fuel to accelerate and decelerate. And remember the fuel trap. More mass means more fuel, which means even more mass. In an exponential spiral, even with massive shielding, the most energetic galactic cosmic rays simply penetrate meters of material as if it did not exist. There is no way to stop them completely without carrying shielding so massive that no conceivable rocket could launch it. Some have proposed using artificial magnetic fields to deflect charged particles, imitating the terrestrial magnetic field. In theory, this would work for the solar wind and lower energy particles. But generating a magnetic field strong enough to protect a spacecraft would require massive superconductors and enormous amounts of electrical energy. The necessary magnets would weigh tons and consume energy continuously for decades. And again, the most energetic galactic cosmic rays have such high energy that even intense magnetic fields barely deflect them. It is like trying to deflect a bullet with a magnet. It works if the bullet is made of iron and moving slowly, but it is completely useless against high-velocity projectiles. The biological damage caused by cumulative radiation is devastating and multifaceted. Prolonged exposure destroys stem cells in the bone marrow, compromising the immune system and making astronauts vulnerable to infections that their bodies would normally fight off easily. It damages the cells of the gastrointestinal tract, causing chronic nausea, vomiting, and malnutrition. It dramatically increases the risk of cataracts, causing gradual blindness. It damages the cardiovascular system, increasing the risk of heart disease and stroke. And perhaps most insidiously, space radiation causes neurological damage. Studies involving mice exposed to simulated cosmic radiation levels demonstrate cognitive impairment, memory loss, and behavioral changes. Astronauts on a journey spanning decades could literally lose their minds gradually, their brains slowly damaged by cumulative radiation until they could no longer function. And all this damage is cumulative and irreversible. It is not like an illness you can cure with medication. Every radiation impact leaves permanent scars on your deoxyribonucleic acid, which your body attempts to repair, but never does so perfectly. Over time, these imperfect repairs accumulate, exponentially increasing the risk of cancerous mutations. An astronaut who survived a 20-year voyage to Proxima Centauri, assuming everything else functioned perfectly, would have a nearly 100% probability of developing multiple cancers. Their life expectancy would be severely reduced. They could suffer from early-onset dementia, blindness, and organ failure. They would be shattered survivors of a journey that destroyed their bodies at the cellular level. Space radiation is not an engineering problem with a technological solution waiting to be discovered. It is a fundamental consequence of existing in a universe filled with energetic particles accelerated by violent processes such as supernova explosions and solar flares. We cannot turn off the Sunday. We cannot stop supernovae in distant galaxies. We cannot eliminate the cosmic rays that saturate intergalactic space. We can only attempt to shield ourselves, and that protection comes with prohibitive costs in terms of mass, energy, and mission viability. Radiation is just one more of the silent killers that make long-distance space travel practically impossible, constantly reminding us that we evolved to live under the protection of an atmosphere and a magnetic field, and that venturing beyond that protection for prolonged periods means subjecting our bodies to destructive forces against which we have no adequate defense. If distance, velocity, fuel, and radiation were not enough to condemn journeys to Uranus and Proxima Centauri, there exists one final, even more relentless killer: time itself. Time is unforgiving. It makes no exceptions, and it cannot be negotiated. Every passing second, every minute, every year, during a space journey spanning decades, mechanical systems degrade, electronic components fail, materials fatigue, and human bodies age inexorably. On Earth, when something breaks, we repair or replace it. When we need supplies, we go to a store. When we become gravely ill, we visit a hospital. But in deep space, millions or billions of kilometers away from Earth, you are completely alone, with only the resources you carried with you upon departure. And those resources are finite, limited by your vessel's payload capacity and the brutal fuel equation. Let us first consider the mechanical systems of a spacecraft. Every component has a limited operational lifespan. Engines wear out, seals degrade, and the life support systems that recycle air and water eventually fail. On the International Space Station, which orbits just 400 kilometers above Earth, something is constantly breaking. Pumps fail, filters clog, and computers reboot unexpectedly. And when this happens, replacement parts can be sent on the next resupply mission. Alternatively, astronauts dedicate hours or days to repairs, using tools and spare parts stored on board. But even so, the International Space Station has required dozens of extravehicular activities for repairs and upgrades. Now imagine a ship traveling towards Uranus for 9 years, with no possibility of resupply. Every spare part must be carried from the start. Every tool, every component that might fail. Electronic systems are particularly vulnerable in the space environment. The radiation we discussed earlier not only damages biological cells, it also damages electronics. High-energy particles strike computer chips, causing what engineers call single-event upsets, where a memory bit randomly flips from 0 to 1, or vice versa. Most of the time, these errors are detected and corrected by redundant systems, but occasionally they cause catastrophic failures. During a decades-long voyage, cumulative radiation would gradually degrade all electronic systems, exponentially increasing the probability of critical failures, and replacing a spacecraft's entire electronics package in flight is extraordinarily difficult, requiring massive spares that add significant weight. Then there is the power problem. Spacecraft require electricity for everything: life support systems, communications, navigation, heating, lighting, and scientific experiments. The Voyager probes draw their power from radioisotope thermoelectric generators, which convert heat from radioactive plutonium into electricity. But the plutonium gradually decays, producing less heat each year. The Voyagers, launched in 1977, will begin to run out of sufficient power in the 2030s, barely 50 years after launch. 50 years sounds like a long time until you compare it to the 73,000 years it would take to reach Proxima Centauri at current speeds. Even with more powerful nuclear fission reactors, maintaining power for centuries or millennia is extraordinarily difficult. Reactors require maintenance, replacement of fuel rods, and perfectly functioning cooling systems. A power system failure means immediate death for any crew, freezing in the absolute darkness of space. The fuel itself also presents temporal problems. Chemical propellants can degrade during prolonged storage. Tanks can develop microleaks that slowly vent fuel into space. Even minute losses of a few grams per day become significant over years or decades. And remember that every gram of fuel counts when you have carefully calculated how much you need to decelerate upon arriving at your destination. Losing even a small fraction of your fuel could mean being unable to brake, condemning you to fly past your destination at thousands of kilometers per second before disappearing forever into the interstellar void. But perhaps the most terrifying aspect of time is its effect on human beings. Astronauts are not machines that can be turned off and turned back on. They are people who age, become ill, and die. A 9-year journey to Uranus means astronauts who depart in their 20s or 30s would be nearly 40 upon arrival. And that is only the outbound trip. If they could somehow return with another 9-year journey, they would arrive back on Earth in their 50s. They would have lost nearly 20 years of their lives locked inside a metal can the size of a small house. Their friends and family would have aged or died. The world they left would be unrecognizable. Technology that was modern when they departed would be obsolete. And all this assumes they survive, that they do not develop cancers from radiation, that they do not suffer accidents, and that they do not go mad from extreme isolation. The psychological isolation of long-duration space travel is a challenge we are only beginning to comprehend. Studies of terrestrial analogues, where people live in isolated habitats, simulating space conditions, consistently show that psychological stress increases dramatically over time. People become irritable, depressed, and anxious. Conflicts among crew members intensify. And these are studies where participants know they can leave at any moment and are only kilometers from home. Imagine knowing there is no possible escape for 9 years or more, that any conflict must be resolved because there is no way to separate. Any psychological problem must be managed with limited resources because there are no psychologists to call and no psychiatric hospitals available. And for a trip to Proxima Centauri, even at optimistic velocities of 20%, the speed of light, which would take 20 years, the temporal challenges multiply exponentially. 20 years is more than 1/4 of an average human lifespan. Astronauts who departed young would arrive middle-aged. Some could die during the journey from natural causes, accidents, or illness. You would need sufficient medical capacity to handle everything from appendicitis to cancers and even childbirth. If the crew includes couples, you would need provisions for decades: food, water, and medicine, all stored under conditions that prevent degradation. You would need recycling systems that function with 100% perfection for 2 decades, because no resupply is possible. A single critical failure at any time would mean death for the entire crew. Time is the patient killer that waits silently while everything else falls apart. It does not need to be dramatic or violent. It simply continues, second after second, wearing down systems, aging bodies, and accumulating small failures until eventually something critical collapses. And in deep space, far from any possibility of rescue, that inevitable collapse is a death sentence. Time reminds us that we are fragile and temporary beings, attempting to traverse distances that take periods longer than our own lives. We are creatures who live decades, attempting to reach destinations that require millennia. And that fundamental disconnect between our mortality and cosmic timescales is another irrefutable reason why places like Uranus and Proxima Centauri will remain forever out of our reach. Faced with all these seemingly insurmountable obstacles, scientists and engineers have proposed bold and revolutionary technologies that, in theory, could make interplanetary and interstellar travel viable. Antimatter engines that convert mass into pure energy with 100% efficiency. Giant solar sails propelled by lasers that accelerate ships to significant fractions of the speed of light. Pulsed nuclear propulsion that detonates atomic bombs behind a vessel to propel it forward. Warp drives that bend spacetime itself, allowing travel faster than light without truly violating Einstein's laws. These ideas sound like science fiction, and indeed, many were popularized by programs like Star Trek, but some have solid theoretical foundations in real physics. The problem is that the gulf between theory and practical engineering is as vast as the distances these systems would need to cover. Let us begin with antimatter, often considered the perfect fuel. When matter and antimatter meet, they mutually annihilate, converting completely into energy, according to Einstein's most famous equation, $E equals mc circumflex, $2. All mass is converted to energy without waste, with 100% efficiency. No other known physical process releases so much energy per kilogram of fuel. In principle, a few kilograms of antimatter could propel a ship to relativistic velocities, but there are monumental problems. First, producing antimatter is extraordinarily difficult and energetically costly. Currently, CERN in Geneva can produce approximately 1 nanogram of antimatter per year using its most powerful particle accelerators. 1 nanogram is 1/1000th of 1 gram. At this rate, producing a single gram of antimatter would take 1 billion years. Second, storing antimatter is nearly impossible because it annihilates instantly upon contact with any normal matter. You would need perfect magnetic traps that keep the antimatter suspended in a perfect vacuum, never touching the container walls. These traps require intense magnetic fields generated by superconductors that consume energy constantly. A single power failure, even for a microsecond, would allow the antimatter to touch the walls, and boom, instant annihilation, releasing all its energy at once. It would be like carrying a nuclear bomb that could detonate at any moment due to any technical failure. Third, controlling the annihilation to produce useful thrust instead of simply exploding is an engineering challenge that no one has solved. You would need some kind of reaction chamber that channels the energy in a specific direction to create thrust while resisting temperatures and pressures that would instantly vaporize any known material. Solar sails seem more feasible because they are conceptually simple. Deploy a giant, reflective sail in space, and the pressure of sunlight pushes it like the wind pushes a ship's sails. This works. In fact, the Japanese Aerospace Exploration Agency successfully launched a small solar sail called Icaros in 2010, which sailed to Venus using only light pressure. But scaling this concept for interstellar travel requires sails the size of entire countries, kilometers in diameter, made of materials thinner than human hair, yet capable of resisting the constant bombardment of micrometeorites without tearing. And the pressure of sunlight decreases with the square of the distance, rapidly becoming useless once far from the inner solar system. To achieve interstellar velocities, you would need to supplement sunlight with enormously powerful ground-based lasers, focused with perfect precision onto a state-sized sail as it moves away at increasing speeds. The Breakthrough Starshot project, which we mentioned earlier, proposes exactly this. Thousands of minisails the size of postage stamps, each carrying minuscule instruments, accelerated to 20% of the speed of light by arrays of ground-based lasers, with combined powers of 100 gigawatts. 100 gigawatts is approximately the output of 100 nuclear reactors. Focusing this massive amount of laser energy with sufficient precision to hit postage stamp-sized targets millions of kilometers away requires incredibly sophisticated adaptive optics. And remember, once accelerated, these probes have no way to slow down. They would flash past Proxima Centauri at relativistic velocities, having mere minutes to gather data before disappearing forever. And all this is for tiny probes, not crude vessels. Scaling to the size needed to carry humans is completely impracticable. Pulsed nuclear propulsion, conceptualized in Project Orion during the 1950s and 1960s, proposes detonating nuclear bombs behind a spacecraft and using a massive pusher plate to absorb the explosion and convert it into forward acceleration. Calculations suggest this could reach speeds of 3 to 5% of the speed of light, sufficient to reach Proxima Centauri in less than a century. But the practical challenges are monumental. You would need thousands of nuclear bombs, each detonating in perfect sequence. The pusher plate would have to withstand thousands of nuclear explosions without vaporizing. Damping systems would have to protect the crew from brutal accelerations that would otherwise crush them. And the political implications of launching thousands of nuclear weapons into space, with the risk of the launch rocket exploding and scattering radioactive material, make this idea politically unviable. And then there are warp drives, the favorite solution of science fiction. The idea is that instead of moving your ship through space, you move the space itself around your ship, compressing space in front of you and expanding it behind, creating a wave of spacetime that carries your ship faster than light, without truly violating relativity, because locally you are not moving fast. Physicist Miguel Alcubierre proposed a mathematical metric for this in 1994 that is consistent with Einstein's equations. But there are devastating problems. First, it requires matter with negative energy density, something we have never observed, and which possibly does not exist in macroscopic quantities. Second, calculations suggest you would need energy equivalent to the mass of entire planets or stars. Third, there is no known mechanism to create or control such a space-time distortion. It is mathematically possible, in the same sense that it is mathematically possible for all the air atoms in a room to simultaneously move to a corner, leaving you in a vacuum, but the probabilities are so astronomically low that it will never happen. All these proposals share a fundamental problem. They are based on physics that we barely comprehend, or on engineering that is centuries beyond our current capabilities. They are not realistic plans. They are theoretical speculations about what might be possible if we overcome challenges that currently seem insurmountable. It is as if Leonardo da Vinci had designed a jet airplane during the Renaissance. He could draw the blueprints, but he would not have the materials, the metallurgy, the electronics, the fuels, or the knowledge of aerodynamics needed to actually build it. It is so far removed from available technology that it is effectively science fiction. And these advanced propulsion proposals are just as far removed from our current engineering. Meanwhile, Uranus and Proxima Centauri remain as distant and unreachable as ever, mocking our ambitions with their mere existence, visible, yet perpetually untouchable. There is an aspect of long-distance space travel that is rarely discussed but is profoundly terrifying: communication, isolation. On Earth, we are accustomed to instant communication. You send a text message, and it arrives in seconds. You make a phone call, and you hear the other person's voice immediately. Even when you call someone on the other side of the planet, the delay is imperceptible, only milliseconds. But in space, communication is limited by the speed of light, and the distances are so vast that delays become not just annoying, but completely incapacitating. A ship traveling to Uranus would be so far away that communications would take hours in each direction. A ship at Proxima Centauri would be so distant that conversations would take years. This communication isolation creates operational and psychological challenges that make missions even more impossible. Let us first consider the basic numbers. Radio signals, which is how we communicate with spacecraft, travel at the speed of light, 300,000 kilometers per second. It sounds incredibly fast until you apply it to astronomical distances. The Moon is approximately 384,000 kilometers from Earth, so radio signals take approximately 1.3 seconds to arrive. Apollo astronauts experienced this delay in their conversations with mission control. They would say something, then wait almost 3 seconds for the response, counting the round-trip time. Awkward, but manageable. Mars, at its closest approach to Earth, is approximately 55 million kilometers. Signals take about 3 minutes in each direction, 6 minutes round-trip. This makes real-time conversations completely impossible. Mars rovers operate with significant autonomy because sending commands and receiving confirmations takes too long for direct control. Uranus, at 2.8 billion kilometers at its closest approach, presents much more severe challenges. Radio signals take approximately 2.5 hours to reach Uranus from Earth. That means 5 hours round trip. If a ship at Uranus sends an emergency message saying something went wrong, mission control on Earth will not know until 2.5 hours later. They must then analyze the problem, formulate a solution, and send instructions back. Another 2.5 hours. By the time the instructions reach the ship, 5 hours have passed since the original emergency. In many scenarios, 5 hours is the difference between life and death. A critical life support system failure, an atmospheric leak, or a fire on board all require an immediate response, not instructions that will arrive in 5 hours. This communication delay means that any ship traveling to Uranus must be completely autonomous. The astronauts and the ship's automated systems must be able to diagnose and resolve any problem without help from Earth. They cannot call experts. They cannot consult manuals they did not bring with them. And they cannot receive spare parts they did not pack. They are completely alone, more isolated than any explorer in human history. Historical explorers who sailed to unknown lands could at least eventually hope to find land, other people, and resources. But space explorers traveling to Uranus would only find absolute vacuum, darkness, and silence. And that isolation would last for years, gradually eroding the human psyche in ways we are only beginning to comprehend. For Proxima Centauri, communication isolation reaches almost incomprehensible levels. At 4.2 light-years away, a radio signal takes 4 years and 2 months to arrive from Earth. That means more than 8 years round trip. If a ship reached Proxima Centauri and sent a message announcing success, Earth would not know until 4 years later. If something went wrong during the approach and they sent a distress signal, no one on Earth would find out until it was absolutely too late to do anything. The astronauts would have been dead for years by the time their emergency message arrived, and any response sent from Earth would take another 4 years to reach the ship, at which point everyone on board would have long since died, and the ship would drift as a silent tomb through interstellar space. This isolation is not just an operational inconvenience, it is a profound psychological challenge. Humans are social creatures who crave connection with others. Even the most extreme introverts need some level of social contact to maintain mental health. Astronauts on missions to Proxima Centauri would be effectively cut off from humanity. They could send messages home, but replies would take years. By the time they receive an answer to their question, the question is irrelevant. The context has completely changed. The people they are asking about could have died in the interim. The world they left would have evolved in ways they cannot anticipate. Every message from Earth would be like a time capsule from an increasingly distant and irrelevant past. And there is an even darker aspect to this isolation. During the journey, especially after passing the halfway point, the astronauts would be closer to Proxima Centauri than to Earth. Earth would be light-years behind them. Proxima Centauri, light-years ahead. They would be literally in the middle of nowhere, further from any possible help than any human being in history. If they looked toward Earth with telescopes, they would see our sun as just one more star among thousands, indistinguishable without knowing exactly where to look. The pale blue dot that Carl Sagan so eloquently described would be invisible, lost in the glare of our star. The feeling of isolation, of insignificance, of being completely alone in the cosmos would be psychologically devastating. Uncrewed robotic probes avoid these psychological problems but face their own communication challenges. Voyagers 1 and 2, currently in interstellar space, beyond the influence of the Sun, send signals so weak that they require the most sensitive antennas on Earth to detect them. As they move further away, their signals weaken proportionally with the square of the distance. Eventually, even our most powerful antennas will not be able to distinguish their transmissions from the background noise of the cosmos. And that is only at the relatively small distances the Voyagers have reached after 45 years. A probe at Proxima Centauri would need incredibly powerful transmitters to send detectable signals across 4 light-years, requiring energy that the limited onboard power sources could hardly provide for decades or centuries. The silence of deep space is another brutal reminder that we are not built for these voyages. We evolved in social groups, where communication is instant, where help is a call away, where we are never truly alone. Deep space reverses all these conditions. Communication has delays of hours, years, or is completely impossible. Help is permanently out of reach, and the solitude is absolute, total, and overwhelming. This isolation, combined with all the other challenges we have explored, makes journeys to places like Uranus and Proxima Centauri not just difficult or dangerous, but fundamentally incompatible with human nature. We are prisoners not only of physics and distance, but of our own biology and psychology that irrevocably bind us to the world that gave us origin. Beyond all the technical and physical obstacles, there exists a final barrier that is rarely discussed with honesty: the absolutely astronomical economic cost of attempting missions to Uranus or Proxima Centauri. The most ambitious space programs in human history, such as the Apollo program, which took humans to the moon, already cost sums that defied imagination. But those costs pale in comparison to what a crewed mission to Uranus, much less Proxima Centauri, would require. We are talking about budgets that would exceed the gross domestic products of entire nations, resources that would have to be maintained for decades or centuries, and investments so massive that no government or private consortium could reasonably justify them when we face urgent problems here on Earth. The Apollo program cost approximately $153 billion in 2020 adjusted dollars. This was for 6 successful missions to the moon, each lasting only a few days, to a destination that is barely 384,000 kilometers away. The program required the work of more than 400,000 people at its peak, including engineers, scientists, technicians, and administrators. It consumed approximately 4% of the United States federal budget during the 1960s. It was a massive national effort justified by the Cold War and competition with the Soviet Union. And all this to reach our nearest cosmic neighbor during voyages that lasted less than 2 weeks. Now, extrapolate these numbers to a crewed mission to Uranus. The ship would need to be orders of magnitude larger and more complex than the Apollo capsules. It would need life support systems capable of sustaining a crew for 9 years or more. It would require massive radiation shielding. It would need nuclear reactors for long-duration power. It would require tons of fuel or advanced propulsion systems that do not yet exist. It would need extreme redundancy in all critical systems because there is no possibility of rescue. The costs of designing, developing, testing, and constructing such a ship would easily be hundreds of billions or trillions of dollars. And that is just to build the ship, not counting the massive rocket needed to launch it, the ground support infrastructure, the years of crew training, and the mission operations over a decade. Some analysts have tried to estimate the cost of a crewed mission to Mars, a destination much closer than Uranus. Estimates vary widely, but conservative numbers suggest $500 billion to $1 trillion for the first mission. Mars is, at its closest, approximately 55 million kilometers, requiring voyages of 6 to 9 months. Uranus is 50 times further away, requiring voyages of 9 years or more. If we simply scale the costs proportionally, although the reality would be much worse, we would reach figures of multiple trillions of dollars. For context, the total gross domestic product of the United States in 2024 was approximately $25 trillion. A mission to Uranus could consume 10 or 20% of the gross domestic product of the richest nation on Earth for years, for a destination where we cannot even land because it is a gas giant. And if Uranus seems economically unviable, Proxima Centauri is in a completely different league. We are not talking about billions, but tens or hundreds of trillions of dollars. The breakthrough Starshot project, which proposes sending postage stamp-sized minisondes to Proxima Centauri, estimates costs of approximately $10 billion just for the initial development and testing phase. And that is for tiny, uncrewed probes that would fly past without slowing down. A crewed mission would require generation ships the size of small cities, life support systems that function perfectly for decades, closed ecosystems, food production capacity, and complete medical facilities. It would be like building and launching a self-sufficient floating city into space. The costs would be so astronomical that no number makes real sense. And these costs are not one-time investments. Long-duration space missions require continuous support for their entire duration. Mission control must remain operational for years or decades, with personnel constantly monitoring the ship's systems, analyzing data, and sending commands. Deep space communication networks, such as the National Aeronautics and Space Administration's Deep Space Network, with giant antennas in California, Spain, and Australia, must be maintained and updated. All this costs money, year after year, decade after decade. A 20-year mission to Proxima Centauri would require maintaining support infrastructure for at least 20 years, probably more. And during all that time, the money is unavailable for other priorities: education, health, infrastructure, combating climate change, and reducing poverty. This is where the economics of space travel clash with political reality. Governments must justify massive spending to citizens who vote and pay taxes, and it is extraordinarily difficult to justify spending trillions of dollars to send humans to Uranus or Proxima Centauri when that same money could solve urgent problems on Earth. We could provide clean water to every person on the planet. We could eradicate diseases. We could build renewable energy infrastructure. We could educate entire generations of children. The tangible benefits of these terrestrial investments are immediate and measurable, while the benefits of long-distance space exploration are abstract and difficult to quantify. Advocates of space exploration correctly argue that investment in space technology generates innovations that benefit society. Communication satellites, global positioning systems, weather forecasting, environmental monitoring, and advances in materials, science, medicine, and computing. All of these are valuable, but there are diminishing returns. The Apollo program generated massive innovations because we were learning how to do completely new things. Missions to Uranus or Proxima Centauri would primarily be the scaling of existing technologies to extreme scales, which is engineeringly impressive, but less likely to generate revolutionary innovations that justify the monumental costs. And finally, there is the problem of political continuity. Missions that last decades or centuries require political commitments that span multiple government administrations. But politicians think in electoral cycles of 2 to 6 years. It is extraordinarily difficult to secure funding for projects that will not show results until long after current politicians have left office. The International Space Station has survived multiple changes in administration, but constantly faces budgetary threats and has been almost cancelled several times. And that is for a facility in low Earth orbit that provides continuous scientific benefits. A mission to Proxima Centauri that would not show results for decades would be even more vulnerable to political changes and budget cuts. The cost of dreaming of the stars is not just money, it is opportunity. Every dollar spent on long-distance space exploration is a dollar not spent on other priorities. And when we face climate crises, pandemics, increasing inequality, and geopolitical conflicts, it is difficult to argue that sending humans to unreachable destinations should be our highest priority. This does not mean we should abandon space exploration completely. Robotic missions to solar system planets, telescopes that study the distant universe, and satellites that monitor Earth, all of these provide scientific and practical value at relatively reasonable costs. But crewed missions to Uranus or Proxima Centauri are so far beyond what is economically viable that they will remain in the realm of fantasy, regardless of whether we eventually solve the technical challenges. We are prisoners not only of physics, but also of the economy that governs how human societies allocate scarce resources among competing needs and wants. And so we come to the end of our journey through the impossibilities that separate us from Uranus and Proxima Centauri. We have explored the incomprehensible distances that convert even our own solar system into a vast abyss beyond practical reach. We have faced the tyranny of the speed of light, that absolute limit that makes our fastest ships pathetically slow on cosmic scales. We have examined the cruel trap of fuel, where every additional gram requires more fuel in an exponential equation without solution. We have described Uranus, that unreachable ice giant, where we could not even land if we somehow arrived. We have contemplated Proxima Centauri, our closest stellar neighbor, which might as well be in another galaxy, given our inability to reach it. We have faced the lethal radiation that saturates deep space, silently destroying cells and electronics during voyages of years or decades. We have considered time, that patient killer that erodes systems, ages bodies, and turns missions into races against biological and mechanical clocks that inevitably run down. We have evaluated bold proposals for advanced propulsion, from antimatter to solar sails to warp drives, only to discover that they all remain firmly in the realm of theoretical speculation, separated from practical engineering by chasms as vast as those they seek to cross. We have experienced the terrifying silence of deep space, where communication takes hours or years, and isolation is total and absolute. And we have calculated the astronomical economic costs that make these missions not just difficult, but fundamentally unviable, given the political and economic realities of how human societies function. Each of these obstacles by itself would make journeys to Uranus or Proxima Centauri extraordinarily difficult, but we do not face just one. We face all of them simultaneously, each amplifying the others in a cascade of converging impossibilities. Distance requires high velocities that need massive fuel, which adds weight, which requires more fuel. Long journeys mean more time exposed to radiation that damages systems and bodies that need repair, which requires spares that add weight. Communication isolation requires complete autonomy that needs redundant systems that add complexity and weight. The costs of solving each problem multiply when they must all be solved together. It is not simply difficult, it is effectively impossible with any technology we can reasonably anticipate developing in the coming centuries. And perhaps the hardest truth to accept is that these limitations are not temporary. They are not engineering problems awaiting technological solutions that we will eventually discover. They are fundamental consequences of the physical laws that govern our universe. The speed of light is an absolute limit. The distances between stars are vast because the universe is vast. Cosmic radiation exists because the cosmos is violent, filled with stellar explosions and energetic particles. Time passes inexorably because that is the nature of time. No amount of technological progress can change these fundamental facts. We can dream of technologies that bend or break these rules, but those dreams are not based on realistic physics, but on hopes that we will discover some cosmic shortcut that we currently have no reason to believe exists. We are, ultimately, prisoners of our cosmic garden. Earth is not just our home, it is our prison, surrounded by invisible yet absolutely effective barriers of distance, time, and fundamental physics. We can look outward with increasingly powerful telescopes. We can detect exoplanets orbiting distant stars, worlds that might harbor life, civilizations, and wonders that we can never fully imagine. We can send robotic probes that will take decades or centuries to reach the confines of our own solar system, much less the stars beyond. But we ourselves, human beings of flesh and blood, with lives that last only decades, will never set foot on worlds orbiting other stars. We will probably never visit the outer planets of our own solar system. We are confined to Earth, and perhaps eventually to a few nearby worlds, like the Moon or Mars, if we have enough luck and determination. But there is a different perspective on this reality. Perhaps our inability to reach the stars reminds us of the precious value of the only world we can inhabit. Earth is not simply a rock in space. It is an extraordinary oasis of life, complexity, and beauty in a cosmos that is mostly empty, cold, and inert. Of the thousands of exoplanets we have discovered, none is as clearly habitable as Earth. Most are toxic hells, frozen deserts, or gas giants where we could not survive for seconds. Our planet, with its oceans, breathable atmosphere, temperate climate, and complex ecosystems, is extraordinarily rare, and it is the only one we have, the only one we will be able to have for the foreseeable future. Perhaps the lesson of our condition as cosmic prisoners is not despair, but responsibility. If we cannot escape to the stars, when we ruin Earth, then we must care for Earth with extraordinary care. There is no backup planet. There are no Martian colonies that will save us if we destroy our oceans, poison our atmosphere, and collapse our ecosystems. The technology that would be required to make Mars habitable is orders of magnitude more advanced than the technology needed to repair the damage we have caused to Earth. If we can terraforming Mars, then we can certainly restore Earth. And Earth has the advantage of already being habitable, of already having functional ecosystems, liquid water, and a breathable atmosphere. Preserving and restoring Earth is infinitely easier and more realistic than colonizing other worlds. And there is beauty in our smallness, in our cosmic fragility. We are minuscule creatures on a tiny planet, orbiting an average star in an ordinary galaxy among billions. The universe is incomprehensibly vast, and we are incomprehensibly small. But in that tiny corner of the cosmos, on this blue planet, floating in the vacuum, we have created art, music, literature, philosophy, and science. We have contemplated the universe and tried to understand our place in it. We have looked at the stars with awe and ambition, dreaming of reaching them, even knowing that we probably never can. And there is dignity in that effort, in that persistent dream, despite overwhelming impossibilities. Uranus and Proxima Centauri will shine there, points of light in our night, constantly reminding us how vast the universe is and how small we are. We will never touch them. We will never walk on their surfaces or those of their moons and planets, but we can study them from a distance, learn about them with telescopes and probes, and allow them to inspire our imagination and curiosity. And perhaps, That is enough. Perhaps the value of these impossible destinations is not in physically reaching them, but in how they push us to ask deeper questions about our place in the cosmos. The impossibility of traveling to Uranus and Proxima Centauri teaches us humble but essential lessons. It reminds us that despite all our technological progress, all our advanced science, and all our ambition as a species, we remain fundamentally limited creatures. We evolved on a specific planet, under specific conditions, and when we move too far away from those conditions, our bodies literally begin to fall apart. Astronauts, who spend only 6 months on the International Space Station, return with weaker bones, atrophied muscles, compromised immune systems, and deteriorated vision. Their spines lengthen in the absence of gravity, adding up to 5 centimeters of height that are then painfully compressed upon return. They lose up to 30% of their muscle mass. Their bone density decreases by up to 10%, dramatically increasing the risk of fractures. And this is after only half a year in microgravity, still partially protected by the Earth's magnetic field, just 400 kilometers from home, where they can be evacuated in emergencies. Imagine the effects of 9 years traveling to Uranus, or 20 to Proxima Centauri. Astronauts would arrive with skeletons so fragile that they could break with the slightest impact. Their muscles would be so atrophied that they could barely move under gravity. Their cardiovascular systems, accustomed to pumping blood without gravitational resistance, would fail under the demands of even the partial gravity of Mars. Their brains would show neurological damage from cumulative radiation, with cognitive deficits, memory loss, and behavior changes. Their eyes would develop cataracts from exposure to cosmic radiation. Their immune systems would be so compromised that minor infections could become lethal. They would arrive not as triumphant explorers, but as shattered survivors of a journey that destroyed their bodies at a fundamental level. We are, in the most literal sense, prisoners of terrestrial gravity, of the terrestrial atmosphere, of the terrestrial magnetic field. These are not mere conveniences that make life more comfortable. They are absolute requirements for our long-term survival. Moving away from them for prolonged periods means subjecting our bodies to conditions for which we are not adapted and against which we have no adequate defenses, and no amount of exercise, dietary supplements, or medical interventions can completely compensate for the absence of the planetary systems that protect and sustain us. But recognizing our limits is not defeatism, it is realism. And realism is the foundation of all genuine wisdom. We can honor our dreams of exploration while simultaneously recognizing the impossibilities we face. We can continue pushing the boundaries of what is possible, sending robotic probes further, building more powerful telescopes, and developing new technologies that gradually expand our reach. But we must also accept that some destinations will forever remain out of direct human reach. And that is fine. The universe does not exist to be conquered by us. It exists independently of our ambitions, vast and indifferent, governed by laws that do not negotiate and make no exceptions. Perhaps the true frontier is not out there among the stars, but right here on our own world. We still do not fully comprehend Earth's deep oceans, where strange creatures live in perpetual darkness under pressures that would crush submarines. We are still discovering new species in rainforests, new ecosystems in underground caves, and new forms of microbial life in the most extreme places. We have yet to solve the mysteries of our own consciousness, of how lifeless atoms organized in certain ways produce thoughts, emotions, and self-awareness. We still do not know how life arose on Earth, how inert chemistry transformed into self-replicating biology. There are enough wonders on our own planet to occupy human curiosity for millennia. And if the destiny of humanity is to remain confined to Earth and perhaps a few nearby worlds, then our moral imperative is to fiercely protect the world we have. There is no escape to the stars if we ruin our home. There is no planet B waiting to receive us with open arms. Mars is a frozen desert with a toxic atmosphere, where every drop of water, every breath of air, and every calorie of food would have to be produced with extraordinarily complex technology. Venus is a hell of sulfuric acid and lead-melting heat. The gas giants have no surface to land on. The moons of Jupiter and Saturn are bathed in lethal radiation or frozen at temperatures that would turn air into snow. Compared to these inhospitable destinations, Earth is literally a paradise, the only oasis of complex life that we know of in the entire observable cosmos. So yes, we are prisoners of our cosmic garden, but what an extraordinary garden it is. A blue planet covered in oceans where life arose billions of years ago and evolved into millions of different forms. A world where water flows liquid, where the climate allows civilization, where chemical complexity eventually produced beings capable of contemplating the universe that created them. We are trapped here, yes, but being trapped on Earth is not a curse. It is our only chance to exist, to experience, to create meaning in a universe that would otherwise be simply physics and emptiness. Uranus will remain there, that impossibly tilted ice giant, spinning sideways as it orbits the Sun on its 84-year journey. Proxima Centauri will continue to shine faintly, too dim to be seen with the naked eye, but present in our telescopes, with its planets orbiting in the habitable zone, worlds that might have oceans and atmospheres, but that we will never visit. And we will remain here, on this small blue world, looking up with awe and longing, dreaming of unreachable destinations, while hopefully trying to learn to appreciate and protect the only destination we truly have. What aspect of these seemingly insurmountable limits of space travel astonished you the most? Leave a comment below to join the discussion about why the cosmos seems so generous in showing itself, but so cruel in keeping itself out of reach. Do not forget to like this video, subscribe to Nocturnal Science, and activate notifications to continue exploring the deepest mysteries of the universe and our condition as creatures confined to a small corner of the cosmos, dreaming of the stars we will never touch.